Hey guys, my name is Rico Rotongjia. I'm a master in robotics student at Northwestern University. Today I'm going to show you my final project, multi-agent coordination between 3 Delta robots. Have fun.
The first thing I'd like to demonstrate is the basic setup of this project. This project is composed of a piebald simulator that resembles a group of 3 Delta robots in real life, and a motion planning pipeline that's based on Arviz and Moveit. The first basic usage is clicking and dragging the object to a desirable pose. And we can do that by simply dragging this marker. And I can tilt it. Notice that the robots are moving accordingly. If, let's say, I'm trying to reach an unachievable pose, say, I'll push it down too much. First of all, we can see there will be collisions, potential collisions, and they're marked in red. And the object is jumping back and forth, meaning we're trying to reach something unachievable. If we let it go, the object will jump back to what it was before we click and drag. And sometimes we may see this huge green projection of the object. That is because right now our CPU usage is very, very high, because we're running Arviz, Moveit, and the simulator at the same time. But in real life, we will not be running the simulator, so this is not really going to be an issue. And we can eliminate this by disabling and re-enabling. The second basic usage is executing the motion plan. So we can, first of all, either hit plan, try to see the plan as a trajectory of waypoints, and click execute. And as we can see here, the robots are moving accordingly. Or we can simply hit plan and execute. Of course, we have reached the goalpost, so there's no full trajectory for that. And we can make our robot go to trigger pose. Let's say we can go this way. This leg is at a fixed joint. Notice that we have 90 degrees. Some joint limits here. That's why we cannot hold the object, for example, more. This leg is at its joint limit, which is 90 degrees. That's why we cannot hold the object even more. Okay, we can go stay once again. Awesome. We're going to enable the goal state. Awesome. And we can hit plan. Now, as we can see, this is the trajectory that takes us from the starting point all the way to the goalpost. One thing to notice is that the robot, let me disable the goalpost first. So at the beginning of the trajectory, which is waypoint 0, that should be exactly the same as this real world configuration, which is being fed into Moveit through TF. So if we want to visualize it, we click scene robots show robot visual. As you can see here. And the waypoint, which is calculated by our planar adapter, gives an exact output as the scene robot, which verifies the correctness of our implementation. And then, as we drag along this little slider, you can see the full trajectory. So now let me disable it. This time let's do plan and execute. Notice that there's a speed difference between the real world control and the trajectory. That is because in real world, our controllers might be a little bit slower or faster. In our case, we're running the simulator and Moveit at the same time on the same computer, and the CPU usage right now is very high. The Pi-Bola simulation simply cannot catch up to the speed of the trajectory. So in real life, if that's not an issue, we can safely disable it. But if we're concerned about the timing of execution, then we can enable it. And the way to disable or enable this feature is done in a Moveit configuration file, as detailed in the user manual. Now let me re-enable the goal pose. And notice that there are 4 markers, but we can only click and drag the one embedded in the object. We cannot drag the other ones. Another part I'd like to mention is about the Pi-Bola simulator. First of all, in this simulator, we have all motors actuated. So if we try to click and drag, we cannot really move the robots. The robots will move back to their original position. We have 3 motors mounted on each robot, and all these motors are mounted at the legs, all of these motors are mounted at the base of each leg. If we disable these motors, as you can see, initially they're lying on the ground, and then they're going to jump a little bit. That is because we have serial elastic actuators mounted right before the joints, right after the motors. And this result has been verified by using Lagrange dynamics implemented on Google Colab. So this project can serve as a very good example in terms of, first, how to build parallel robots in Pi-Bola. Second, how to mount 3 of the robots in a single environment. Third, how to mount an object attached to these robots. And fourth, how to build a serial elastic actuator. But more importantly, this project is a great example, and if not one of the first examples, to show how to build parallel robots in Moveit and get the motion planning pipeline to work with it. And also, we have 3 robots here. Coordination between these robots are also tricky. So we have a high-level IK and a low-level IK. The 2 are being chained all together in a motion planning adapter. One thing that might be an improvement in performance is using Moveit Visual Tools, which is created by Picnic. But that would require more setup in its code. Finally, it's worth mentioning that we can actually have a quote-unquote headless mode, which is to disable the GUI of PyBullet. We can do that by declaring direct mode of PyBullet. This makes the setup more CPU friendly. Now you might be wondering, can I see the robot? The answer is yes. So we can turn on Show Robot Visual under Scene Robot. This directly shows the robot configuration that comes directly from the PyBullet setup. So, like that. Thanks for watching.